This is lab 4, circuits and capacitors. In this lab, we're going to explore how circuits behave with resistors and capacitors in various configurations using an online virtual lab. We're going to predict these behaviors using our knowledge of the loop rule and conservation of current, and then we're going to make actual measurements of these values at various locations along the circuits that we create. And then we're going to observe charging and discharging of a capacitor and make associated calculations. Some important physics principles involved would be the loop rule and the definition of steady state as it pertains to current conservation, and also knowledge about charging and discharging of capacitors and the formula for capacitance, and also Ohm's law. So using this online virtual lab, we're going to construct a couple of different circuit configurations, and that would be first a simple series circuit, and we're going to make measurements of the current and voltage using ammeters and voltmeters, and then calculate resistance of each of the elements. And then we're going to create an RC circuit with 2 bulbs, a battery, and a capacitor to charge and discharge the capacitor. So first, in the series circuit, I measured the current throughout it to be 0.02 amps at all locations as expected due to conservation of current. And then using Ohm's law, I predicted that it would be 0.0204 amps, which is what I also measured. And then the potential difference at various locations is shown here and verifies that the loop rule holds because they sum to 0 as you make a loop around the entire circuit. And then also note that the potential difference across the ammeter and the wire are 0, and this means that they're considered ideal, so their resistance is 0. So when you put the resistor in parallel with an ammeter instead of in series, the effective resistance of that resistor is closer to 0 in this case because the ammeter has 0 resistance, and the current increases to 0.06 amps. In charging and discharging a capacitor, I observed that the light bulb shines brightly and then gets dimmer until it goes out entirely, and the current slows down until it appears to stop. It took about 10.8 seconds for the capacitor to charge with the 10 ohm light bulb and about 19.5 seconds with a 20 ohm bulb. And then likewise for the discharging process to occur, it took about 10.8 seconds with the 10 ohm bulb and 19 seconds with the 20 ohm bulb. We're able to derive a time dependence relationship of the voltage across the discharging capacitor using knowledge about capacitance and potential difference and charge on the plates, and make a few substitutions and take the derivative with respect to time and see that the current throughout the circuit equals the negative derivative of the charge on the plates with respect to time as the capacitor is discharging. And so using these measurements of potential difference across the capacitor at various times, we can plot the natural log of the potential difference at a time over the potential difference at time 0 versus time, and the slope of this graph will have a value of -1 over RC, and here RC is considered the time constant of the battery, and that means that this is the time at which the voltage difference across the capacitor is 1 over E of its original value, and I calculated that to be roughly 6. So in conclusion, some scenarios to consider: if I'd used an actual ammeter instead of an ideal simulated one, it wouldn't have 0 resistance. It would impact the potential difference along the circuit the same way that any other resistor would, having its internal resistance. And likewise, if I'd used a real battery, it would also have an internal resistance of its own. And if that were the only resistor in the circuit, then depending on the amount of resistance in it, the charging of the capacitor may take more time or less time than what I expected. So if the internal resistance of that battery is less than the 10 ohm light bulb that I used, then the current in the circuit would be higher than what I measured, and it would take less time for the capacitor plates to reach full charge.